Okay, guys, so here's J-19, and I'm about to do this, just two examples, and there's Delta Math practice. It'll be really short. But before that, I just wanted to give you a little bit better demonstration of why this formula is true. I have it all written out, so I just want to look at it real quick. So, okay, so this is just not focusing very well. Okay, well, I just wanted to show, this formula that we did in the last video. I think it's more clear to understand why it's true and way more direct if we just use the fundamental theorem of calculus. Okay, so off to the side, if I let, so here I've got this accumulation function, but but the way that it's defined is that the input of the accumulation function has to be input into another function, h, before it's used. So, yeah. So if I do this, guys, we know that, okay, well, if I do this, let capital G be any antiderivative of lowercase g right here, which means that G prime would give you G. Okay, so let that sink in for a second. So G is any antiderivative of, capital G is any antiderivative of lowercase g. And by any antiderivative, it means like the plus c at the end could be any number. Okay, so if we have that established, then I could just, the way that you compute an integral is you use the fundamental theorem of calculus. That's where you open up these brackets, you take the endpoints of the interval that you're integrating over, you put them at the end here, and then inside of these brackets goes the antiderivative of this. So capital G of W, which I defined over here. Then the way the fundamental theorem works is that you plug the top in here, and then you plug the bottom in here, and you subtract them. Okay, so using the fundamental theorem, I get this other way of representing f, the same accumulation function from the beginning. And then if I want to take the derivative of this f, which I do, I'm trying to show you why this is true. Then, well, for this part here, a is a constant. So you plug a constant into a function and it spits out another constant. So I'm about to take the derivative of this, and keep in mind that this is a constant. And then for taking the derivative of this term, guys, we've been doing this a lot for a long time. This is a chain rule situation. The chain rule is the same thing as in and out. And so the inside is h of x, the outside is g of blank. So the derivative of f, for the chain rule part, it's h prime of x, and then g prime of blank, and then h goes back in. But then, guys, remember how I defined capital G. Capital G is any antiderivative of lowercase g. So if you take the, so therefore G prime is equal to, capital G prime is equal to lowercase g. So this G prime here, I just replaced with lowercase g, and there you have this formula. Okay, I think that's a lot nicer way. And even like if you forgot this formula, you could figure it out the way that I just did with the fundamental theorem. Okay, so I wasn't happy with the last video, so there's that. Okay, this will be short. So accumulation functions as antiderivatives. This is super useful once we get into problem solving more with AP type problems. This is going to come up all the time. So any differentiable function, okay, meaning its derivative exists, any differentiable function can be expressed as an accumulation function. Okay, and then here I am doing this right here. So if f is differentiable and x equals a is in the domain of f, it could be any number in the domain of f, the domain is the inputs, then f of x is equal to f of a plus the integral from a to x. Okay, so a is the you know, this number in the domain that you know. X is the input, and then this right here, this is f prime of w dw. And guys, very often you will see, like delta math especially, if I give you delta math problems with accumulation functions, they will use t instead of w. I chose to use w because it is so atypical. It's kind of unusual to use as an input, and I wanted it to be unusual because I didn't want you to mix up like putting x here by accident. This variable, whatever variable you use here in this part of the accumulation function, needs to be different than the input. Okay, and I've explained why before. I won't, you know, take up time saying it again. So the graph of f prime, the derivative of f, is shown in the graph below. If f of 3 equals -2, what is the value of f of 7? Well, guys, you could just use this formula. So basically, you want to know you have the graph of f prime, and you're asked to find a value of f. So you're asked to find a value of the antiderivative of this. So you could just say to yourself, well, I know from this formula here, even though I only have the graph of f prime, I don't have f, but I still want to find a value of f, evaluate f at 7. Even though I don't know f, I know this formula, okay? So, and we know f is differentiable because this is f prime, there's the derivative. So I could use this formula. I could say that f of x is equal to f of some input that you know the output for. So I'm going to use 3 here, plus the integral from 3 to x, f prime of w dw. Okay. So then, so I've got f of x is equal to f of 3 is -2. -2 plus the integral from 3 to x, f prime of w dw. Okay, let me come down here. So I want f of 7. So f of 7 is equal to -2 plus the integral from 3 to 7, f prime of w dw. Guys, right here, this is the area under the curve. So it's the area under the curve f prime. So I go up to my picture and I find the interval 3 to 7, right here. And I want the area under, I want that area there. Okay, it's going to be negative. Now, for the height, so the area of a triangle is 1/2 base times height, and right there we have the height. It's just 2 units. All right, so this is -2 plus, now this is the area under the curve. This is going to be 1/2 base times height. Oh, but it's negative. Okay, I'll fix it. Yeah, let me fix it now, because it's going to be minus. All right, so the base of the triangle is 1, 2, 3, 4, and then the height is 2. So this is -2 minus 4. -6. So f of 7 is -6. Okay, I'm almost done. Now this is the same idea, but just different phrasing. So you don't have to stick with me the whole time, you know, if you feel like you've got it. But the function f is shown below. If g is an antiderivative of f such that g of -6 equals -4, what is the value of g of 0? Well, guys, g is an antiderivative of f. If g is an antiderivative of f, they're telling you that f is equal to g prime. That's what they're telling you there. So this graph of f, that's the graph of g prime. So I want G of 0 here. So I'll go down here. So I'll use this formula, and I'll do it like a little bit faster, I guess. Well, no, let me take my time. Okay, so G of x is equal to G of -6 plus the integral from -6 to x G prime of w dw. Okay, that's the formula. That's this formula from the beginning. I'm just using G instead of F was in the formula. Okay, and this is equal to G of -6 is -4 plus the integral from -6 to x of, guys, G prime is F. G prime is F. So F of W, right? G prime is F. And so I want G of 0, this is -4 plus the integral from -6 to 0, F of W dW, that's -4. All right, and then for this part, I've got to do the area under the curve. So you locate -6 and 0. There they are. So we're doing the area of that triangle. And the height of this triangle is, you just drop any perpendicular, so that would be the height. And it's positive this time. All right, yeah. So the interval is forwards, it's not backwards, and that's above the x-axis, the area, so it's totally positive. 1/2 base times height. All right, the base is 1, 2, 3, 4, 5, 6. So the base is 6, and the height is 4. -4 plus 12 equals 8. So G of 0 is 8.